Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In today's video, we're going to be talking about intermolecular forces. Now, in order to understand intermolecular forces, you need to understand the difference between two vocabulary words, and that is intramolecular forces versus intermolecular forces. The previous one, intramolecular forces, are the forces that happen inside a molecule, namely chemical bonds. So this bond right here, this bond right here, and this bond right here are all considered intramolecular. Okay? Our discussion today is going to be intermolecular forces, and that's the forces that exist between molecules. For example, if I had a CH4 with another CH4, there's a force that actually exists between those molecules. So they're not chemical bonds. It's actually the force that occurs between two molecules of methane. And that's our topic for today. Now, in order to understand the forces that exist between molecules, you actually have to understand the intramolecular forces, or how it's bonded, to fully understand intermolecular forces, of which I'm going to abbreviate as IMFs, intermolecular forces. So let's go ahead and talk about the bonding that exists between these three molecules. Okay, I got a molecule of methane, which has a boiling point of negative 162 degrees Celsius. So that's the temperature at which it changes from a liquid to a gas. So anything above negative 162 will be a gas. And we're at room temperature, so methane at room temperature will be a gas. The next molecule I have is water, and it has a boiling point of 100 degrees Celsius. Okay, so at 100 degrees Celsius, it changes from liquid to gas. Okay, so at room temperature, 25 degrees Celsius, we're at a liquid. Okay, and then we have sodium chloride here at the end, which has a boiling point of 1,465. It's like super, super hot. Sodium chloride at room temperature is a solid. So we got a gas, a liquid, and a solid for these three different chemicals. And a lot of that has to deal with their intermolecular forces. Okay, so let's go into great detail about the bonding that exists, because there's some differences in bonding between these molecules. Okay, now depending on who you talk to, some people may say that this is not polar covalent, but there is a slight electronegativity difference between carbon and hydrogen. So the dipole is very small. Okay, however, the geometry here is tetrahedral, and therefore this dipole, this dipole, this dipole, and this dipole, they all cancel out because this molecule is symmetrical. And since it's symmetrical, the dipoles cancel out, and the dipoles cancel out, we say that this molecule has what we call a zero dipole moment. Now, what that means in regular terms is that this molecule has no part of it that's positive and no part of it is negative. Really, the distribution of the electrons we can kind of think of as like a perfect circle. Okay, there's no electron distortion within a methane molecule. Okay, now when we take a look at the water molecule, it also has polar covalent bonds. Okay, but it also has these lone pairs, and this is actually going to be bent. Okay, so the dipoles are not going to cancel out. Okay, so we're going to say that this is going to be asymmetrical. And it has a non-zero dipole moment. Okay, so it has one. It has a dipole moment. So if you want to think of the distribution of the electrons here, there's going to be a part of it, it's kind of almost look like a lobe. The electrons are going to be more on one side of the molecule than the other. Here, let me redraw that a little bit better. I'm going to do it in the opposite direction to line up with what I have here. So we're going to say that this part kind of look more like this, okay, as far as the distortion, okay, of the electron cloud. Okay, and then finally, this thing doesn't have polar covalent bonds at all. This thing is ionic. Okay, there's going to be a complete transfer of electrons, so we're going to have a full positive charge and a full negative charge that exists between these ions of sodium and chlorine. Now, what we're going to talk about is how a methane interacts with another methane, how a water molecule interacts with another water molecule, and how an ionic compound interacts with another ionic compound. And the story is very simple, okay? The more positive and negative your items are, okay, the more the attraction is going to be between those things, okay? So let's go ahead and go through each of these different types of intermolecular forces, okay? And then we're going to talk about, what's going to increase their magnitude, okay? The easiest one to talk about is ion-ion. So we're talking about something that looks like sodium chloride. So sodium chloride would be an example. And remember, sodium is positive, okay, and it transfers its electrons over to the chlorine, and we get something that looks like this. We have a full octet over here. As far as a Lewis model, this is what it looks like. And what you're finding out here is we need to know all this stuff about bonding in order to do intermolecular forces. So if you're not great at bonding, please go back and watch a couple of my videos on ionic and covalent bonding, and as well as if a compound is polar or not. That's going to be very important as far as having that base understanding in order to do intermolecular forces. Okay. Now, when you have ion-ion interaction, okay, it's really not something that looks like this. In fact, when you have ion-ion interaction, a lattice is formed. So it's going to look more kind of like this. Okay, so if we take a look at this black one right here, remember positive ions are really small, negative ions are really big. Really, this picture is just this portion right here. And what you're going to find out is that these black spheres, okay, they don't just bond to, just one chlorine. They're bonding to several chlorines, okay? One to the left and right, okay, going towards you and out and on top and on bottom, okay, if this lattice was to continue, okay? So this is really what's going on. So if we want to break any of these forces, they're really all chemical bonds, okay? And that's going to increase, that you're going to have to really supply a lot of energy to break things that are fully charged. So things that have the most positive and negative, if you're going to try to break those things, you're going to require tremendous amounts of energy. So as far as our interactions are concerned, the ion-ion interaction is the strongest, okay? And the way you increase it is by increasing the charge. For example, I'm talking about sodium and chlorine. That's a positive one and a negative one. What happens if I had magnesium oxide, okay, which is positive 2s and negative 2s, okay? Or aluminum and nitrogen, which is positive 3s and negative 3s, okay? The interaction here is much stronger than here, and this interaction is stronger than here due to the charges, okay? So as the charges increase, the magnitude of the ion-ion interactions, okay, is going to increase as well. So if I have a whole bunch of aluminum chlorides, okay, aluminum nitrides, here, I'm going to try to offset it here. This is what we would call an ion-ion interaction, okay? So it's not just bonded here, but it's going to be bonded here, and it's going to create some type of lattice that looks similar to what I have in my hand, okay? So ion-ion interaction, that's going to be the highest type of interaction that we have, and that's why we have it listed as number 1, okay? Now, the next highest would be when we have something that's fully charged, ion, to something that is partially charged. Now, when I have this word dipole in here, we mean something that has a dipole moment. So let's take a look at a water molecule, because a good example of ion dipole would be sodium chloride interacting with water molecules, okay? This is an ion dipole interaction, okay? So what I have here are some water molecules, and I want to talk about how the electron cloud is distorted in a water molecule, okay? So if I have a water molecule here, okay, I lined it up, it looks bent, so the red is the oxygen, okay, and the hydrogen is the white. And as you can see, because of the dipoles, the electrons are being pushed towards the oxygen, as well as having lone pairs around here. That means that the oxygen side of the molecule is partially negative, okay? And the symbol that we use is a delta sign to show partially negative. So this is kind of like where the oxygen would be. The hydrogen end is going to be partially positive because all the electrons are being pushed towards the oxygen. So if you will, if I could kind of put in here, it looks something like this. It's kind of like how our water molecule would look like. Okay, so the hydrogen end would be the positive end, and then the oxygen end would be the partially negative end. Well, if you have two water molecules lined up next to each other, maybe something that looks like this. Let me try to do that one more time. Maybe a distortion. That's a little bit better. So remember, this is partially negative, and this is the partially positive side. Well, if you have partially positive next to partially negative, this interaction is what causes it, okay? Now, if you line this up over here to an ion, that interaction is going to be stronger because this is fully charged, okay, where this side is only partially charged, okay? So just wanted to talk about that a little bit. So when you have an ion next to something that has a dipole moment, okay, that's going to be the second highest type of interaction we have. And the example would be like a sodium chloride molecule next to a water molecule that has the partially positive and partially negative side. Okay. Now the next two, okay, are kind of the same. Hydrogen bonding is actually a special dipole-dipole. So I kind of want to write that down. A special dipole-dipole interaction. We'll come back and talk about what makes it special, okay? So let's take a look at these water molecules again, okay? What this part right here is a dipole-dipole interaction. This part would be dipole-ion interaction. So if we had our water molecules, once again, here's a water molecule and here's a water molecule. Remember, the partially positive end of the hydrogen is going to be attracted to the partially negative end of the oxygen, okay? And there's going to be attraction that exists between these two molecules, okay? Now, since they're water molecules, okay, they are going to belong to the hydrogen bonding piece of this, but I want to kind of like talk about how that's different than the dipole-dipole, because these are kind of a little confusing to understand. So let me try to explain the differences between the two. So I'm going to do H2S instead, because we're going to have that molecule here with this molecule here. Now, H2O and H2S look exactly the same, okay? In fact, S and O are in the same column, so they have the same number of valence electrons and everything. Same geometry. All I'm doing is substituting out the oxygen for sulfur down here. This interaction that exists right here and here is what we call dipole-dipole interaction, because both of these molecules have a dipole moment. And you might say, well, Mr. Heffel, what happens if we just switch it over to oxygen? Now, isn't that true? Don't these interactions exist? And they do, but they're no longer called dipole-dipole, okay? What we do is we call this a special type of dipole-dipole. It's going to be called hydrogen bonding, okay? So this part right here, this interaction, is the hydrogen bonding part. And I'd like you to write this down somewhere in your notes, okay? Hydrogen bonding is not a bond, okay? It's an intermolecular force. It's what exists between molecules, okay? So it's not a bond. This is a bond, okay? But we call this an intermolecular force, but we give it the name hydrogen bonding. And that's what makes it so confusing, okay? So once again, hydrogen bonding, it's not a bond, okay? It's an intermolecular force. It just has a terrible name called hydrogen bonding, okay? Now, how do you know when you have hydrogen bonding versus dipole-dipole, okay? It's when hydrogen bonds with either nitrogen, oxygen, or fluorine. So we see this hydrogen, and it's bonded with either nitrogen, oxygen, or fluorine. It's oxygen in this case. And what happens is that this partially positive side right here, the partially negative side right here, is very partially negative. And this side is very partially positive. And this side is very partially positive, which makes this interaction special, okay? So it's due to the high electronegativity value of nitrogen, oxygen, and fluorine. These are some of the highest electronegativity values that you can find on the periodic table, and they're very small. Okay, so once again, how to differentiate between hydrogen bonding and dipole-dipole interaction is that in order to have hydrogen bonding, the hydrogen has to be bonded to the oxygen, but the hydrogen bonding is actually the interaction that occurs between the molecules. So once again, hydrogen bonding is not a bond. It's an intermolecular force that exists between molecule A and molecule B. Like kind of like this part right here would be the hydrogen bonding, okay? And once again, it only occurs when hydrogen is bonded to very electronegative elements of nitrogen, oxygen, and fluorine. And what that does, it creates a very partially positive end of the molecule and a very partially negative side of the molecule, and that makes that interaction right here very, very strong, different than if these guys were sulfur. So if these guys go back to sulfur, it's no longer hydrogen bonding between the molecules because it's not super partially negative and it's not super partially positive, and therefore we would just call this a normal dipole-dipole interaction. Okay, so I'm going to come in here and I'm going to write down H2O attracted to H2O would be a good example of hydrogen bonding. But if I just switched the O's to S's, the interaction between those two molecules, okay, is just going to be called dipole-dipole. So hopefully I did a good job of differentiating the two. A lot of students mess up on this part, so hopefully if you were a little confused, maybe rewind the video and just listen to it one more time, because students get stuck on these differences between hydrogen bonding and dipole-dipole. So when I talk to my students, I just say, hey, hydrogen bonding is just a special type of dipole-dipole, and that's when hydrogen is bonded to something like nitrogen, oxygen, or fluorine, as in the water example. And I think water is going to be the most common one that you actually see. Okay, so let me erase all this stuff here. Okay, and the last one we have are called London dispersion forces. Okay, London dispersion forces occur in all molecules. Okay, so it occurs in sodium chloride, it occurs in water, but when you have something like methane where it doesn't have any of these other types, okay, even the methane has London dispersion forces. Okay, and the way it works is, if we had two molecules of CH4 here, it looks like, well, if their electron clouds aren't distorted at all, okay, that there's not going to be any interactions in between here, okay? But what happens is that these electrons around the methane, they're not static, they're moving, okay? So if you kind of think of like, electron clouds as, kind of like jello, that might be a good example. So if we distort this cloud just a little bit, maybe not the extreme over here, but maybe we push the electrons kind of over there just a little bit, okay, and we create just a small partial negative side and a small partial positive side, well, that will do the same thing to this one. It will start to distort it, and this will be the partially positive side, and this will be the partially negative side. And there will be a tiny little interaction between those molecules, and that's what we call London dispersion forces. Okay, so all electron clouds can get distorted a little bit because they're not like super rigid or stiff. They can fluctuate just a little bit, and those little fluctuations are called induced dipole moments. So it's not a full dipole moment, it's kind of like an induced dipole moment. And there are some electron clouds that are easier to distort than others, okay? So molecules with more electrons, which is a larger molar mass, will have more London dispersion forces, okay? So the more electrons you have, the more the ability to distort the electron cloud is increased, okay? And the word for that, it's kind of technical, okay, called polarizability. So things with large molar mass, with lots of electrons, their electrons can be distorted more easily, creating these induced dipole moments, and therefore have a small intermolecular force called London dispersion forces. Okay. Now, these are the different types of intermolecular forces that you have. there's two rules that you're going to have though. So it's going to be molar mass versus, the type of intermolecular force. Okay. So if you want to think of London dispersion forces as $1 bills and dipole-dipole forces as $5 bills, you could increase the molar mass enough to where you get several of these $1 bills that it might trump the forces of a dipole-dipole if there's a low molar mass here. So when you're determining the overall IMFs, it comes down to two things. So overall IMFs come down to two things, okay? It comes down to type versus molar mass. Because like I said, if you have a large enough molar mass, you might have enough of these $1 bills to trump the dipole-dipole forces. Our next video is going to talk about this discussion between the types of intermolecular forces you have versus the molar mass. And we'll take a look at several examples so that you get a good idea of the overall IMFs. This video, however, is only trying to discuss the differences between the types of IMFs and which ones are the strongest. The last thing that I'd like to leave you with is kind of just some semantics and some vocabulary. Technically speaking, we should really only consider these as IMFs because they're all molecular, okay? As soon as you cross this line right here, these things are going to be ionic because you can see both of them have ions in them, and therefore we should really call them interactions. But this idea of that there's a force that exists between one molecule and another, the word interaction talks about all five of these, okay? But technically speaking, if we use the term intermolecular force, okay, we really should only be talking about things that are covalent, and that would be items 3, 4, and 5. So I like to use this word interaction, okay? How does one molecule interact with another molecule? Instead of the term IMFs, so that I can be all inclusive instead of just talking about items 3, 4, and 5. Okay, so that's just some semantics, word choice between the two. Okay, if you found this information helpful, please give it a like and subscribe. And when you add that comment, it really does push this information out to other students that are interested in learning chemistry.